Welcome to The Explainer. Today, we're going to talk about a formula that's at the very heart of how AI learns to think ahead. It's a core concept in artificial intelligence called the Bellman Equation.
So let's start with a puzzle. How do you actually teach a machine, a robot or maybe a character in a game, to make the best choice right now to get the biggest possible reward way, way down the line? It's all about this tricky balance between what's good now versus what's best in the long run.
Well, the solution to that puzzle is found in this incredibly elegant little formula. It's basically the mathematical backbone for making smart, sequential decisions, and it's called the Bellman Equation. It's really a foundational idea in the whole field of reinforcement learning.
All right, so here's how we're going to break this down. First, we'll look at that big picture reward puzzle. Then, we'll lay out the rules of the game. After that, we'll get into how you can put a value on any situation, and we'll uncover the one-step-ahead secret that really makes this whole thing click. Then, we'll see how to find the absolute best path. And finally, we'll see how this equation actually leads to real-world action.
Okay, so let's start with that core problem. Imagine you're teaching an AI to play chess. Now, a really simple, short-sighted way to do it would be to just grab an opponent's piece whenever you can, right? For that immediate reward. But we all know that's a terrible strategy. A truly good move isn't just about what happens next. The AI has to think many, many steps ahead to actually win the game. And that is the challenge of sequential decisions.
So, to solve this kind of long-term puzzle, an AI first needs to understand the world it's in. We have to define the game board, and all of its rules.
And in AI, this framework is called a Markov Decision Process, or MDP for short. You can really just think of it as the instruction manual for the agent's universe. It's a way to model any situation where an agent has to make decisions, and the results are a mix of what the agent chooses to do and, well, a little bit of randomness.
Now, every MDP is built from just 5 key ingredients. First, you have states, which is just all the possible situations the agent can find itself in, like every single layout of pieces on a chessboard. Then you've got actions, which are all the possible moves the agent can make. Next is transition probability. That's the chance you'll land in a new state after you take an action. Fourth is the reward, the points you get right away. And finally, there's the discount factor, which is this clever little trick to make rewards you get sooner more valuable than rewards you get way off in the future.
So, with all the rules of the game in place, the next big question is, how do we figure out how good it is for our agent to be in any particular spot? How do we even keep score?
We do that with something called a value function, and it's a simple but really powerful idea. We just assign a numerical score to every single state. This number basically represents the total future reward the agent should expect to get if it starts from that state and follows a certain strategy. A high value means you're in a great spot. A low value, well, not so much.
And this leads us right to the core insight, that eureka moment from the mathematician Richard Bellman. It's a really clever recursive trick that makes what seems like an infinitely complex problem surprisingly simple. Bellman called this the principle of optimality. The idea is actually pretty simple, but it's profound. He's basically saying that if you've already found the absolute best path from point A to point Z, then the path you take from any point B along the way, well, that also has to be the best possible path from B to Z.
This recursive property is a complete game changer. It means we don't have to map out all possible futures forever. Instead, we can define the value of where we are right now based on just 2 things: the immediate reward we get plus the value of where we'll be just one step from now.
It boils down to this. The value of your current state is simply the immediate reward you get for your next action plus the discounted value of whatever state you end up in next. It breaks this massive problem of calculating the entire future down into a simple, repeatable, one-step calculation.
This specific formula has a name. It's the Bellman Expectation Equation. Its whole job is to evaluate a strategy you've already decided on. So you give it a plan, and it tells you the value of each state if you follow that plan. It answers the question, so how good is this specific plan I have?
But, just evaluating a plan is only half the battle. What if we don't even have a plan? What if we want to find the absolute best path possible, the optimal strategy? How do we make that leap from good enough to perfect?
And that's where the Bellman optimality equation comes in. The expectation equation, like we just said, evaluates a policy you already have. The optimality equation, on the other hand, it finds the best possible policy. It doesn't follow a plan, it creates the best one.
The secret sauce here is one simple but incredibly powerful change: adding a max operator. Instead of just following a given policy, the optimality equation says, at any state, look at all your possible actions. Calculate the future value for each one, and then just pick the action that gives you the maximum value. It's like being greedy in the smartest possible way.
Okay, so that's the theory. But how does all this abstract math actually teach an AI to do something useful in the real world? Let's try to make it a bit more concrete.
Let's use a classic example, a grid world. Just picture a robot on a grid trying to get to a goal. To encourage it to find the shortest path, we'll give it a small negative reward, like -1, for every single step it takes. But when it finally reaches the goal, it gets a big positive reward, like +10. So here's how an algorithm like value iteration puts the equation to work. It starts out by setting the value of every single square to 0. Then it just goes through the grid over and over again. For each square, it uses that Bellman optimality equation to calculate a new, better value based on the values of its neighbors. It updates the square's value, and then it just repeats this whole process until the values stop changing. At that point, the values have converged, and they reveal the optimal path to the goal.
This recursive iterative logic, it's the engine behind so many famous algorithms in reinforcement learning. Value iteration, policy iteration, and especially things like Q-learning and SARSA, they all use this core Bellman principle to learn. This is the stuff that powers AI that can master games, control robotic arms, and optimize all kinds of complex systems.
So, let's pull all this together. First, the core idea is to break down a super complex future into 2 simple parts: the reward you get right now plus the value of the next state. Second, this lets an agent find the best path not by seeing the whole future, but just by looking one step ahead. Third, the optimality version does this by always choosing the action with the maximum possible value. And finally, this whole principle is the bedrock of modern reinforcement learning algorithms like Q-learn.
Ultimately, the Bellman equation gives us this incredibly powerful tool for assigning a value to any sequence of decisions. So I guess the question for us is, where should we point it next? What is the next great puzzle for AI to solve?